Okay, it's a great pleasure to have our next speaker, Ash Clark from the University of Chicago. So he's going to talk about non-Hermitian quantum dynamics from sensing to novel topology.
Great. So like the other speakers, let me start by thanking the organizers, both for bringing us together to this wonderful place and for the opportunity to speak. So I know it's a pretty diverse audience, so let me start by giving a bit of context. So by training, I'm a condensed matter theorist. These days, I tend to be very interested in driven dissipative quantum phenomena, in condensed matter systems, in quantum optics, in the kind of superconducting circuits that Michael Hattridge was telling us about. I thought, given the audience, though, I would try to sort of tell you about two stories that hopefully resonate with a lot of what the principal interests are in this, among this group. And so the two stories I want to tell you about, the first is a topic that I think has been relatively hot in the area of non-Hermitian quantum dynamics in the last year or so. It's the idea that maybe you could use non-Hermitian dynamics in some coupled mode system to make an amazing sensor, right? And maybe these sensors would even be useful in quantum regimes. So the first story I'll tell you is actually very, very simple. Let's think about those ideas and let's just do some honest calculations. Let's really think about the role of fluctuations. Let's think about how this might work in quantum regimes and see if there really is something here to gain. And so the story I'll tell you, to give the punchline away to begin with, the conventional story that having an exceptional point leads to magical things, that doesn't really hold up in the quantum regime. But there's another way of using non-Hermitian dynamics to give you something really nice. And that key resource is non-reciprocity. And so what I mean by that, I'll define in that first part of the talk. And if there's time that's left in the second part of the talk, I'll tell you about something that sounds even crazier. So we got interested in this question, is there a bosonic or a photonic analog of a Majorana fermion? Is that something that we can make sense of? And so that led us to think about a model, a kind of bosonic version of the canonical model of Majorana fermions in condensed matter physics, the Kitaev chain model. And the surprising thing about this model, there are many, many surprising things, but maybe for this audience, the surprising thing is this is a completely Hermitian Hamiltonian whose dynamics is actually in one-to-one correspondence with a well-known non-Hermitian Hamiltonian. So actually the Hatano-Nelson model for asymmetric hopping in a tight binding chain. So in the last part of the talk, hopefully I can tell you a bit about that work. And I would be remiss, of course, if I didn't mention my collaborators. So this first story on the non-Hermitian sensing, that was really the work of my postdoc, Kiro Lau. And the second story about bosonic Majoranas and effective non-Hermitian dynamics, that's been done with a graduate student of mine, Alexander MacDonald, and I guess my former colleague back at McGill University, Tammy Parekh-Barnea. Okay, so let's launch into this first story, sensing. I'll start by telling you something that actually connects to what Michael was already telling us about. And it's about a very, very generic kind of measurement strategy, the idea of a dispersive measurement. So the idea for this measurement strategy is you have some resonant electromagnetic system, you have some parameter that you're interested in, and this parameter basically sets the position, the frequency of one of your resonances. So depending on this parameter epsilon, the resonance is either shifted to the red or to the blue in terms of frequency. If you can actually see that frequency shift, you can estimate this parameter. So this is a really generic kind of sensing approach that used in all sorts of systems. So quantum mechanically, this is probably the best way to read out superconducting circuits, superconducting qubits. We'll hear more from that in Michael's talks. Even in kind of classical regimes, you can build sensors that detect the presence of viruses using this kind of approach. Okay, so the question is, if there was a way to improve this measurement strategy, that could have enormous applications. Okay, so the first thing you could think about is, one resonance is good, but how about many, many resonances, many, many modes? So you could think about a generalized kind of dispersive measurement, where you have many interacting, coupled, linearly coupled modes. So here, A1, A2, A3. They have many resonances. And the parameter of interest, this epsilon, it could both shift the frequencies of those modes. It could also change the coupling. So generically, your parameter of interest couples to these modes, described with some coupling Hamiltonian of this form. When you change epsilon, you change the positions of resonances. So without epsilon, with epsilon, blue becomes red. And the question is, how best to build a system like this? given a particular coupling to my parameter that I'm trying to sense, how do I get the biggest possible frequency shift? Right? Because you would think that would make for the best sensor. And then the question you could ask is, well, wait a second, is getting the biggest possible frequency shift when I turn on epsilon, is that really the same thing as having the best possible sensor? Or do I need to think about that a little bit more? Okay, and so again, the thing that has gotten a lot of attention, especially in the last year because of some experiments, is the idea that having effective non-Hermitian dynamics could give you a really nice handle on this problem. So here are, again, my different cavity modes, my different resonances. I can imagine just some kind of classical coupled mode theory where the amplitudes in each of those modes, what I'm calling alpha I, their dynamics are described by some effective non-Hermitian Hamiltonian. Okay, if I have M modes, this H tilde is some M by M non-Hermitian Hamiltonian. And so the idea is, okay, maybe if I start when epsilon is 0 by having a degeneracy in those modes, having the perturbation break that degeneracy could actually give me a really large response. And so if I think about just a Hermitian system and I have a degeneracy between two modes, I'd have this effective 2 by 2 Hamiltonian. Without epsilon, the modes are degenerate. With epsilon, the modes split. The amount of the mode splitting is just proportional to the size of the perturbation. Okay, so the mode splitting goes like epsilon. And so then this nice idea, really pioneered by Jan Wiercik, was, well, what about a non-Hermitian system where I have a degeneracy, where that degeneracy corresponds to an exceptional point? So here's the canonical kind of two-mode description of one of these exceptional points. I have two modes that are coupled in a Hermitian way with some coupling J. I have loss and gain, loss on one mode, gain on the other modes. If I start by balancing everything, which is what I have when epsilon is 0, J is tuned to be the same as this gain-loss rate gamma, and then I introduce epsilon to break the degeneracy, move away from the exceptional point, then you get a lot more bang for your buck. So now the splitting of the modes from having an epsilon doesn't grow like epsilon, it grows like the square root of epsilon. And if epsilon is really, really small, square root of epsilon is much bigger than epsilon. Okay, so on the surface, hey, this seems great. For the same perturbation, this system is going to give you a bigger splitting of your resonances. Okay, and again, this is something that's been tested in two recent experiments. I won't go through the detail. There's an experiment from Lan Yang's group at Washington University, which is shown here. I guess an experiment from the Christodoulis group as well. And so again, in a kind of whispering gallery mode resonator, bringing in some kind of external fiber tips that were first able to sort of achieve this kind of exceptional point, and then bring in another tip to basically break that degeneracy and get this kind of mode splitting that grows like the square root of epsilon. Okay, and so this is just basically showing as a function of this perturbation strength epsilon, right, how much of an enhancement in the mode splitting are you getting? So the kind of amplification factor, if you want to call it that, how much bigger is the mode splitting than it would be if we just had a Hermitian system that's sort of the square root of J divided by epsilon, and that's what they're showing here. Okay, so it looks great. You're getting a bigger mode splitting for the same epsilon. The question you could ask is the one I already asked before. Let's be a bit careful here. Does a bigger frequency shift necessarily imply a better sensor? Is that all I need to worry about, or is there more to really thinking about this problem? And of course, there is more to be thinking about this problem, otherwise I wouldn't have much to tell you. So what is it that we have to add to this story? Well, the first thing is we have to really ask what the right question is. Okay, and the right question is not turn on epsilon, how big is the splitting of the modes? The right question to ask is, I'm looking at some noisy output of my system, so how are you going to measure these frequency splittings? You're going to drive your cavities, your modes, you're going to look at the light or the microwaves coming out. What you measure is going to be some noisy signal. It's going to take you some time to be able to tell, does this noisy signal correspond to epsilon equals 0 or epsilon non-zero? So the correct question to ask is not, hey, how are these modes shifting with epsilon? The correct question to ask is, how long does it really take me to distinguish having a perturbation and not having a perturbation? Okay, and to address that question, you crucially need to think about fluctuations in this system. Okay, so for all the kinds of systems that I'm thinking about this sort of physics in the systems where people are doing experiments, there's a price to pay for having a non-Hermitian Hamiltonian, right? And the price to pay is basically what the fluctuation dissipation theorem tells us. So if I have a non-Hermitian Hamiltonian, whether you like it or not, you have damping, you have gain. There must be fluctuations associated with that. Okay, so classically, if I have damping, the fluctuation dissipation theorem tells me I'll have fluctuations that are proportional to that damping rate and the temperature. Quantum mechanically, even if temperature is 0, I have to worry about vacuum noise. Okay, so this is important because to do a good measurement, the noise in the measurement record will obscure the signal you're interested in. And by trying to use this non-Hermitian physics, I'm basically bringing in more noise into my system. So the question is, do you actually win, right? Bigger mode splitting, but maybe worse fluctuation physics. Okay, so that's the statement of the problem. So again, the resolution here and what we have to do, there's nothing really that complicated. So the first thing is, how do I apply the fluctuation dissipation theorem to this system? If you give me some non-Hermitian Hamiltonian that at some classical level describes your coupled mode theory, how do I figure out what the fluctuations are? How do I figure out what the fluctuations are at a quantum level? Okay, so the simple idea is, let's take the non-Hermitian part of the Hamiltonian, the anti-Hermitian part. You could always diagonalize that. We would get some positive eigenvalues, some negative eigenvalues. So I could always think of this matrix as the difference of two positive definite matrices. Okay, so the positive eigenvalues of this non-Hermitian Hamiltonian, those are telling me about gain processes, right? And so I could represent that by a positive definite matrix, y dagger. And then the negative eigenvalues of this thing here, that's telling me about loss. So I could represent that as negative a positive definite matrix, z dagger. Okay, so you can't stop me from doing that. Why would I do that? The idea is now I'm going to, associate those matrices y and z with some physical meaning. Okay, and the idea is, how did you get the non-Hermitian physics in that Hamiltonian? You couple to some dissipative baths. Okay, and the coupling to those dissipative baths, that's exactly what these y and these z matrices are. Okay, so the idea is now to represent where that non-Hermitian physics came from. These y and these z matrices are really telling me there's a bunch of gain baths, there's a bunch of loss baths that you've coupled to. The matrix elements of y tell me how strong those couplings are. Once I have that description, I basically know how to sort of add the noise physics associated with that non-Hermitian Hamiltonian. Okay, so what we basically do is, our non-Hermitian Hamiltonian, look, the dynamics is definitely local in time, so this is a Markovian system. So I'm going to represent everything, all of the dissipative physics, by Markovian dissipative environments. Okay, so kind of using standard tools from whether it's quantum optics or open quantum systems, I can basically turn this non-Hermitian coupled mode equation into a fully conserving open quantum system description of my system. So I now have a set of Heisenberg quantum Langevin equations, which I think have come up in other talks. So as opposed to these amplitudes, I have lowering operators for each of my modes. Here's the non-Hermitian Hamiltonian. And now the fact that I got the non-Hermitian parts of this thing from these couplings to baths, associated with those couplings are noise terms. Okay, and these noise terms, they're basically the operator equivalent of Gaussian white noise. These noise terms now will tell me how fluctuations enter my system. It'll tell me how fluctuations limit my ability to make a measurement. Okay, so one thing that is hopefully clear, this equation here is definitely not unique. You give me a non-Hermitian Hamiltonian, there's an infinite number of ways I could find a y and find a z. Okay, and what that tells you is, right, it's not necessarily a horrible thing. It tells you, if you want to exploit this non-Hermitian Hamiltonian to get the best possible sensor, you want the least possible noise, you better find the y and the z that give you the smallest possible noise entering the system. Okay, so the fact that this is not a unique way of representing our system as an open quantum system, that makes perfect physical sense. There are many, many dissipative settings that would give you exactly the same averaged equations of motion. We're really interested here in understanding what's the best possible that we can do in terms of the noise physics. If you give me a given non-Hermitian Hamiltonian, I want to be able to tell you how to construct the Y and the Z, the couplings to these environments, that give you the smallest possible noise. And everything we've done is really focused on the quantum regime. All of this could work in classical settings too, where your noise is not vacuum noise, it's thermal noise. Okay? So that's the, the part where how fluctuations kind of enter. The other part is to really model a measurement a bit more carefully. So not just to say, okay, I have these resonances, the resonances shift. What do you actually do in an experiment? Okay, and what you actually do, or what we focused on, is very similar to what Michael was talking about in his talks. So how am I going to see the fact that these resonances are, shifting? I'm going to couple one of the modes in my coupled mode network to some input-output waveguide or transmission line. I'm going to send in light into the system, in the simplest case at one frequency, and look at the light that comes out. Okay, and that reflected light is going to have information on this parameter epsilon I'm interested in. Okay, so generically, if you look at the amplitude of the output light, that's this B out here, there'll be a piece that sort of depends on epsilon. For small epsilon, it's just going to be linear in epsilon. So the ideal thing to do is to basically multiply this output field by a phase factor and then measure its real part. That has all of the information that you want about epsilon in it. Okay, so in optics, this is known as a homodyne measurement. This is something that is done all the time. You might wonder, okay, this is one particular thing you could do. You can actually prove this is the optimal thing to do. Okay, so there's a quantity known as the quantum Fisher information, where you can really ask, of all the possible things I could measure about the light coming out of my cavity, what's the best possible thing to measure to learn about epsilon? It really corresponds to this kind of measurement. Okay, I won't go through the details of that, time is short. Okay, so the last thing is given, okay, we've got the fluctuations, we're modeling a real measurement, the thing that you're measuring is this homodyne current, right? How do we actually quantify how well the measurement is doing? Okay, so this is what you see in the experiment. You see a bunch of noise. To learn about epsilon, what are you going to do? You're going to average. You're going to take the time average of that output current for some measurement time tau. And the hope is that by doing that average, you kind of average away the noise, you leave the signal. So what this plot here is showing as a function of time, what is happening to this averaged homodyne current. And the idea is the solid lines are the average value. So if epsilon is 0, on average, this quantity m is 0. If epsilon is non-zero, on average, m has some value that's growing as a function of time. Yep. Well, that's what I'm about to describe, right? That's what the shaded region is. So the average value is represented by these solid lines here. This shaded region here is representing, if you want, the variance in this quantity m, right? So when I integrate up this I of t, there's still going to be some uncertainty in what the value of m is, and that's what this shaded region here is describing. So in the long time limit, so time is much longer than any time scales associated with the dynamics, the difference between the averages grows as time, and the size of the variance, the width of these uncertainty regions, it's just a diffusive process. It grows as the square root of time. So a natural thing to ask is, what's your signal to noise ratio, right? How big is this separation compared to the width of those distributions? And that's something that's basically going to grow nearly in time. Okay, so if you average for longer and longer and longer and longer, of course, your measurement gets better and better and better and better. So what's the right question to ask? The real right question to ask is, how long do I have to wait before I have a signal-to-noise ratio of 1? If I fix the size of the perturbation I want to measure, epsilon, how long is it going to take me to decide whether that perturbation is there or not? Okay, and that's the thing that we want to sort of understand and kind of develop bounds for. Okay, so the first thing we could think about is, let's forget about the noise for a second, and let's just ask about the signal, right? So how big is the difference of the average of this quantity m with epsilon and without epsilon? And do I actually gain something just in terms of the size of the signal by doing this exceptional point stuff? Okay, so the simplest thing you could imagine doing is just having a single cavity. And again, this is my input-output waveguide. I'm looking at the light reflected off the system. when I drive it. The parameter of interest in this one mode case, there's not much it can do. All it does is couple to the frequency of that mode. So in that case, you can see in an optimal setting, how big is the signal power? So the difference here squared. It grows quadratically in time. And it also is proportional to, when you drive the system, how many photons do you put in there? Because again, if I want a huge signal power, if I just drive harder and harder and harder, I can make my signal as big as I want. So to have a reasonable question to ask, we need to constrain how much power you're using for the measurement. Okay, so if you just do a conventional dispersive measurement with one mode, the signal power grows as epsilon squared times squared, and is proportional to how many photons do you actually put into the cavity. So the question is, if we now go to this kind of two-mode setup, where the parameter of interest now changes the coupling between these modes. So just like in the experiments I told you about, do we do better, right, in terms of the signal power? Okay, and the crucial thing to sort of realize, which is a really simple point, the quantity that you have to look at is not what do the mode eigenvalues do. The crucial thing you need to look at is what's the susceptibility of the system. Okay, so this, if you want, is basically the inverse of the non-Hermitian Hamiltonian. It's the Green's function. It has many other names as well. It's this quantity, which I'm going to call the susceptibility matrix, that's going to be crucial. So if you just go through the math, what is the signal power now? It's the signal power we had for our simple one-mode sensor, with a bunch of stuff involving chi. Okay, and the question is, can that bunch of stuff actually be big? How do I make it big? Okay, so the simplest case to consider is, imagine I have a reciprocal system. So by reciprocal system, formally I mean that this susceptibility matrix, the 1-2 element and the 2-1 element are exactly the same. So if you hit mode 1 and ask how mode 2 responds, that's exactly the same thing as hitting mode 2 and asking how mode 1 responds. Okay, another way of saying it is that in my non-Hermitian Hamiltonian, I have some couplings here. Those coupling terms should have the same magnitude. So in that reciprocal case, you find that there's a fundamental bound on how big your signal power can be. It can be bigger than what you have for just a single mode system. And the prefactor there is just chi1,1 squared. So again, chi is this simple Green's function or susceptibility. Chi1,1 basically says, if I drive mode 1, how much does that amplitude actually respond? So great, you could have a really big signal power if you make chi1,1 really big. Does this have anything to do with an exceptional point? And the short answer is not really. So making chi1,1 really big really corresponds to just making an amplifier. It means that if chi1,1 is really large, if you send signal or power into this system, it's going to come back with gain. More photons will come out than what you put in. Yeah? Sorry, I didn't. So delta in this thing here, this is actually the frequency of the drive that you're applying. So I'm assuming that you're coherently driving the system at one frequency. You have a choice both of how strong that drive is. That's going to determine this photon number that you induce. And you have a choice of what's the frequency of that drive. And in an experiment, you'd imagine picking the optimal value of that drive frequency. Okay, and all these bounds I'm talking about, they apply no matter what that frequency is you pick. Okay, so the upshot here is, if you have a reciprocal system, you can get a really, really big signal power, but you need to build an amplifier. You need to have a system where whatever you put in, a lot more stuff comes out. Okay, and this plot here, time is short, I'm not going to go through the details. The blue curve here is for a simple two-mode system where you tune to an exceptional point. You see that the signal power relative to a one-mode system, it's bigger than 1, it's decent. The orange curve is the same kind of two-mode system where you're nowhere close to an exceptional point. And the only point to take home is the peak of the orange curve is not so different than the peak of the blue curve. Okay, so having an exceptional point, it's not so crucial for this kind of measurement. Having gain is important. Okay, but all of this is about signal power. I told you the thing we care about is signal to noise, right? So what about the noise physics? Okay, and so again, the signal to noise ratio, here's our plot of how to think about our integrated measurement output. We want to sort of understand how big is that separation compared to these widths here? Okay, and that ratio, that signal-to-noise ratio, it's going to get bigger the longer I average. So the signal-to-noise ratio is proportional to your averaging time. The thing that I care about is this rate, or if you want, this inverse time scale that multiplies things, this gamma. Okay, and so the question is that something that I could really make larger by having a non-Hermitian system? Okay, and again, the thing to keep in mind is to optimize this quantity, it's going to be crucial to pick the right way of implementing your non-Hermitian physics in terms of coupling to dissipative baths. Okay, so if you stick to this Hermitian system, and again, I'm focusing on this very simple two-mode kind of sensor, like the experiments that came out late last year. Two modes, the perturbation of interest is a coupling between the two modes. If you stick to a reciprocal system, so that is without the perturbation, H21 and H12 have exactly the same magnitude, so there's no inbuilt directionality. And this rate here that tells me how quickly does my signal-to-noise ratio grow, it's fundamentally bounded by how strongly did you couple to this input-output waveguide, that's what this kappa is, and how many photons do you use for the measurement. Okay, whether you're at an exceptional point, even whether you have gain or not, it makes no difference whatsoever. So gain was really good for increasing the size of the signal. It doesn't help the signal-to-noise ratio. Why is that? Well, I think as Michael has already been telling us, in the quantum world, amplification comes with a price. Amplification always involves extra noise. So even though you make your signal enormous by basically building an amplifier, no matter how you implement that non-Hermitian physics, you're also going to involve injecting a whole lot of extra noise. So when you compare the size of the big signal against the size of the big noise, you don't really do any better. Okay, so this might seem incredibly depressing. Non-Hermitian physics seemed like it would help us. We thought about the fluctuation physics. It seems like it's not helping us. How can we still use non-Hermitian physics to do something interesting? Well, there's no reason we need to have a reciprocal sensor. Okay, so the idea now is the same kind of setup, but imagine through some miracle, I could construct a coupled mode system where without the perturbation, with no epsilon, H12 is non-zero, but H21 is zero. So that violates the condition I wrote earlier, this condition for reciprocity. In this sort of system, where again, without the perturbation, it's definitely non-reciprocal. When you put the perturbation in, this kind of reciprocal coupling, you break the directionality of the system. The fundamental bound there is actually different. In that case, this measurement rate can be made parametrically bigger than what you could ever do in a reciprocal system, what you could ever do in a one-mode system, by just making this non-reciprocal response, the response going from mode 2 to mode 1, bigger and bigger. Okay, so the upshot is making this susceptibility matrix element also gives you an enormous signal, but quantum mechanically, I'm not forced to have extra noise by having that non-reciprocal response be very large. Okay, and I do want to get to the last part, so just to illustrate that concept, focus on this plot over here. So this is this measurement rate. How quickly is my signal-to-noise ratio growing? Again, for this simple kind of two-mode sensor. The x-axis here is what's the frequency of the drive you're using to make your measurement. The blue curve here is basically if you use a reciprocal system. I think this dashed curve here is you tune exactly to an exceptional point. The blue curve is you're away from an exceptional point. Again, it's a reciprocal system. This is that fundamental bound. You can't beat the bound. Okay, the exceptional point, maybe you get a bit closer to it, you're still bounded by it. If you have a non-reciprocal system, where again, without the perturbation epsilon, things can only go from 2 to 1 and not vice versa, you can beat that bound by a large amount. Okay, so there is something useful for sensing in a simple non-Hermitian Hamiltonian. Non-reciprocity is the key ingredient. Okay, so this all might sound fine and well at the level of theory. You can't stop me from writing a Hamiltonian like this, where H21 is missing. You might wonder, how would you actually achieve this in an experiment? And again, I don't have time to do it justice, but there's a huge community of people interested in basically realizing these kinds of non-reciprocal couplings. So the theorist's PowerPoint view of how you would do this, I would go buy a chiral waveguide, a waveguide where photons can only go from the right to the left, and I would couple my two modes to that waveguide. And if I do that in the right way, that gives me exactly this kind of one-way coupling that I want. Okay, so it turns out with a little bit more work and PowerPoint skills, you can actually realize this sort of situation in a lab. One way, the most easiest way, is to buy the kind of circulators that Michael was talking about in his talk. So if you put circulators into your system, you can realize this sort of coupling. There are also all sorts of other interesting ways to effectively get this kind of effective non-reciprocity. Okay, so you're basically mimicking having your two cavities coupled to some kind of chiral waveguide. Okay, so the upshot is, for this first and main part of the talk, non-Hermitian physics can be useful for this kind of generalized dispersive sensing. The key thing is not having an exceptional point or tuning close to an exceptional point. The key thing that could be a resource is actually using non-reciprocity. Non-reciprocity gives you a way of having an enormous enhancement of signal without any fundamental constraint that there must be added noise associated with that as well. Okay, so the clock says I have 4 minutes, and so 4 minutes seems like the perfect amount of time to both completely change directions and tell you something that sounds a little bit crazy. So let's all take a bit of a breath. And so now let's write something that looks totally different and totally distinct from sensing or non-Hermitian physics. So let's jump gears and let's, return to my condensed matter roots. Let me start by just reminding you about the very basic physics of this Kitaev chain model. Okay, a model that is, it's fascinating a large portion of the hard condensed matter community. So what do you have? You have spinless electrons on a one-dimensional tight binding lattice. They can hop from site to site. And there's also this superconducting pairing potential that can add and remove particles on adjacent sites. So why is this so amazing? Well, as Kitaev noted, the right way to think about this model is not to think of it in terms of electrons, but to actually think of it in terms of Majorana fermions. So write your electron lowering operator in terms of its real and imaginary part. And if you do that, and if you pick a particular value in parameter space, so imagine this T and delta are matched, you find something kind of amazing. So again, each electron is now a gamma A and a gamma B. It has two parts, two kinds of Majorana fermions. You find that there's this funny kind of dimerization. For each electron, the B Majorana is coupled to the A Majorana to the right and not to the left. Okay, so in a very incomplete way, this leads to all sorts of beautiful physics. You have these Majorana modes that can be unpaired at the end. This is a great way to encode a qubit to do topological quantum information. The question that we're basically asking is, well, could I do this with bosons? Okay, and again, the simplest thing you could do is say, well, take this Hamiltonian here, it's quadratic Hamiltonian. You can't stop me from saying those C operators are bosonic operators. It turns out that's not interesting at all. Okay, and so again, very quickly, why is that not interesting? If I write the fermionic model in momentum space, this is what it looks like. I can write it as in this sort of 2x2 form. The kinetic energy goes like a cosine. It's like a sigma z for this 2x2 Hamiltonian. The pairing term goes as a sine. Okay, and so a way of seeing there's something topological about this model is as you change k, the sigma z term and the sigma x term have a difference dependence on k. The Hamiltonian represented as a vector can have some winding. Okay, so what goes wrong with the bosonic case? In the bosonic case, a term like this, C dagger k, C dagger minus k, if k goes to minus k, that's exactly the same term, right? Because the bosonic operators commute with one another. So in the bosonic case, this term here can't be a sine k, it's got to be a cosine k. So now from the point of view of topology, this would be super boring, right? If both terms go like cosine k, I can never get any winding in this plane here. So it looks like we're stuck, there's nothing interesting to do. There's a simple fix. Well, I need to have a cosine k on the pairing term. Why not change the kinetic energy? Why not make that a sine of k? So now I have cosine k, sine of k, sigma z, sigma x. I could still get some winding. So if I go into real space, what does that correspond to? It corresponds to, again, it looks exactly like the standard Kitaev model, but you've put an I in that hopping phase. Again, this is a completely Hermitian Hamiltonian, okay, but that I actually changes everything in the bosonic case. Okay, So again, 30 seconds, I need to make a connection to non-Hermitian physics. So this model has some amazing properties. I'm just going to tell you about one of them. If I write now my bosonic model in terms of these quadrature operators that Michael told us about, so again, if you want like position and momentum, the real and imaginary part of the lowering operators, I see the same kind of structure I have in the fermionic model. X is only coupled to P's, and there's a kind of spatial asymmetry, right? So if T is equal to delta, X is basically only coupling to P on the adjacent site. And I'll take one more minute and then finish up. So again, it looks very, very similar to what you have in the fermionic case. But what are the implications of this? And the most striking implications are in terms of dynamics. So if I look at the equations of motion, again, for these quadratures, think of them as half a photon, I see X's are only coupled to X's, P's are only coupled to P's. I see equations that are sort of asymmetric spatially. So xj is strongly coupled to xj minus 1. So this is how I've defined this e to the 2r factor. It's weakly coupled to xj plus 1. So in terms of dynamics, what would this give me if r is very large? Here's my photon. I split it into the x and p parts. This dynamics would say the photon sort of splits. The x goes to the right and the p goes to the left. Okay, so this is a very funny kind of propagation. There's a kind of chirality in the system. Do photons go to the right or the left? It depends on their quadrature. Are they an x or a p? It depends on their phase. So this is sort of like the physics of the spin Hall effect, where does an electron go to the right or to the left? It depends on its spin. Here it depends on the quadrature. And finally, I'll make the connection to a non-Hermitian Hamiltonian and Professor Hatano's work. The nice thing here is this is really unitarily equivalent to 2 copies of a non-Hermitian type binding chain, where the hopping matrix element from left to right is different in amplitude than the hopping matrix element from right to left. Okay? So again, you're getting effective non-Hermitian dynamics. Hopping is stronger in one direction than the other direction. Starting from a completely Hermitian Hamiltonian, in 10 seconds, where does that come from? Even though I have a Hermitian Hamiltonian, the dynamics of my system, if I work out the equations of motion, I have to look at the dynamical matrix of my system. That dynamical matrix is not Hermitian. Okay, so in general, these bosonic models that don't conserve particle number give you a natural route to explore the dynamics of non-Hermitian models in a way where you don't need any external dissipation. Okay, and that's something that we're continuing to pursue. So anyways, hopefully I gave you a taste of this, this last topic. I'm happy to chat more about it if anyone is interested. I'm just going to flash up my conclusions, and thank you for your time.
Actually, maybe you explain of mind the exceptional point. Why it is necessary for the exceptional point?
So why does the okay? So there's a very simple answer to that.
Okay.
And I have to go back a bit to find it. So in terms of just, what are you doing at the end of the day with these measurements? You're sending in light and stuff is coming out. Yeah. So what do you care about? You care about the response of your system. Yeah. The response of your system is controlled by a Green's function, which is just a linear system. That Green's function is the inverse of the Hamiltonian, more or less. That knows about its eigenvalues and its eigenvectors. So simply focusing on what the mode eigenvalues do doesn't tell you the full story, right? I also need to know what, if you want, the left and right eigenvectors are doing, right? So look, maybe it would have worked, maybe it didn't work. You do an honest calculation, and you see that the crucial thing is either having gain or having non-reciprocity. So it's more than just the eigenvalues that matter for this style of measurement. That's the simple answer.
Okay, so something to ask you. The exceptional points are necessary for the non-Hermitian system. Without exceptional points, there is no need to explain in the other way around the non-Hermitian physics.
So I'm not saying exceptional points aren't interesting for anything. I'm saying for this particular kind of sensing, right, there's actually something better that you could do to have an enhanced sensor.
Yeah, actually something to say is a non-Hermitian physics. There is a fractional values of winding number. Okay, I have also got the same thing for the Hermitian Hamiltonian.
But I'm not talking about winding numbers here. This wasn't about topology. It was
simple. Yes. But I am not able to understand why the part of the non-Hermitian physics reflecting in the Hermitian system?
So that is something, again, I was at a different model, and that was the thing at the end here. So it's a simple thing that I think is well known by some people and not by others. When you have a bosonic system that doesn't conserve particle number, quadratic Hamiltonian, the Hamiltonian is Hermitian. When you work out the equations of motion, the Heisenberg equations of motion, the dynamical matrix, right, d by dt of this two vector of operators, the effective Hamiltonian that shows up here is not this Hermitian Hamiltonian. It's actually that times a kind of sigma z. This is actually a non-Hermitian Hamiltonian, or a non-Hermitian matrix. So that's the correspondence. The dynamical matrix in these bosonic problems is non-Hermitian.
Thank you very much, Many.
So you mentioned that, if you want gain, then there will be noise. And so in the case of EP, there is going to be issues. Is there a microscopic understanding of non-reciprocity which shows that implementing non-reciprocity does not get you noise?
Yeah, so I was sort of quick about that, but so this system here, which was a way of getting this non-reciprocal coupling I want, everything in this setup is passive. So all I have here is a chiral waveguide, right? Give me the luxury to imagine that we have something like this. So photons just go from right to left. And all that happens is a photon that's in this waveguide could hop into this cavity and come back out. There is no process here that involves gain. There's no process that actually creates excitations in the system. So quantum mechanically, it's the processes that give you gain by creating pairs of excitations. If you want two-mode squeezing processes, those are the ones that necessarily have noise. If you have something completely passive like this, even if it's a funny passive system, where, again, in this chiral waveguide, things go in one direction, I don't need to have any noise. And if you work out the details of this microscopically, you really see there's no need to have added noise.
Any other question?
Yeah, so I'm asking that how in the Kitaev model, the kinetic part is now imaginary. So how your system is actually physically reflecting that?
Good. So physically, that going from a cosine to a sine from a cosine k to a sine of k, that corresponds to making your tight binding hopping matrix element purely imaginary.
Yeah.
So you could ask, how am I going to do that?
Yeah.
How am I going to tell Michael to build this? Because this really could be built with a superconducting circuit. It's a bunch of parametric amplifiers. To build this, it's easier to actually make a gauge transformation and to move this I into the phase of the order parameter, into the phase of the pairing. And when you do that, what you find is, you find a model where the hopping is purely real. But then this pair potential, this delta, basically changes sign from bond to bond. So it's positive delta, positive delta, negative delta. So that's a completely gauge equivalent description. That would be the easiest way to realize this. Because in a photonic system, to generate this kind of term, this involves some external driving, right? This is one of those parametric amplifier interactions. So why not just use that external driving to get the phases that you need? So physically move the I by a gauge transformation into the delta, and that's the way you could control the phases.
Okay, and you also said that there will be some dissipation of particle number, so that is because of that term, right?
No. So the nice thing about this model, and look, we can realize non-Hermitian physics using dissipation, that we know. The nice thing about this model is I don't need any dissipation whatsoever, because at the end of the day, this is an honest-to-goodness Hermitian Hamiltonian, right? It could be realized with zero coupling to dissipative environments. So you don't need any dissipation here.
I see. Okay, thank you.
Maybe I could just comment. I mean, the imaginary hopping, if you did this in cold atoms, it might not be a big deal. So when they realized the Haldane model using fermions, I mean, they jiggle the optical lattice to make a complex
So
phase.
the point is, if you're willing to realize this hopping through an active process, sure. If it's an active process, there's some other drive whose phase is important. In this system, though, this definitely has to be an active process. It'd be nice if this was passive. Right? And so the implementation I'm talking about, this could just be some static passive coupling. It doesn't involve any drive. And again, if you move this I into this order parameter, the driving that you need to generate these terms also gives you that right phase. But you're right. You could just realize that hopping term actively and get a phase that way.
Maybe if you turn on Feshbach resonances, you get the pairing or something.
Yeah, maybe there's a way of doing that way too. Yeah.
Maybe one last question.
In the first part of your talk, we were mentioning the noise, and you had these bounds.
Yeah.
These are bounds within Fermi's golden rules, sort of, or could you say this is really second law?
So I should have said this more carefully. So everything I was doing, the perturbation I'm interested in, this epsilon, everything was assuming that we're basically perturbative in epsilon. So you're interested in understanding a very, very, very weak, change to your Hamiltonian, and so you're basically doing linear response. And so all of linear response is controlled by this Green's function. This is just, simple algebraic bounds coming from the form of that Green's function and these constraints on, what's the smallest amount of noise I can have given a particular way I've realized the dissipative dynamics. But yeah, doing this non-perturbatively is also something you can do. That's something we have started to have results on. Yeah.
So I couldn't catch how non-hermiticity tumbled out of the Hermitian Hamiltonian.
Yeah, and I agree. I was very quick on this part here.
Yeah.
So the way it came out was I stopped looking at just the Hamiltonian itself. You stare at that as long as you want. It's definitely Hermitian, right? But what I did instead was ask, what's the dynamics of this system? What are the equations of motion? And then the interesting thing is the equations of motion, right? The dynamical matrix, if I combine, working in momentum space here, my lowering operator, my raising operator into this vector, the matrix that basically generates time evolution for these operators is a non-Hermitian matrix. Okay, so now I could either understand this as dynamics coming from this Hermitian Hamiltonian, or I could say, hey, look, I have some effective non-Hermitian Hamiltonian. These are amplitudes of, two 1D fields, 1D chains described by some non-Hermitian Hamiltonian. So the idea is that in these systems, the Hamiltonian and the dynamical matrix are distinct. The dynamical matrix is the thing in the equations of motion. That is non-Hermitian, even though the Hamiltonian is Hermitian. And that's why, if you want these systems where you have parametric driving, let me go back to, where I'm adding pairs of particles, they can be unstable dynamically. It's a parametric instability that Michael was talking about. You can get exponential growth in these systems. How do you get exponential growth from a Hermitian Hamiltonian? Well, it's that dynamical matrix, which is non-Hermitian, that can have complex eigenvalues. Okay, so it's something that's really well known in other communities. I don't think people have really thought to exploit the correspondence to all this work on effective non-Hermitian dynamics. Yeah.
Thanks.
Yeah.
So sorry, maybe probably it's a very very similar question. So if you go to the next the Hatano kind of equation, right? That is in X and P,
right.
And somehow it was very important that it is in X and P to get these equations, right? But the Hatano equations, they were in A's and A daggers. But if you do that, you don't get this equation.
Yeah. So what I'm basically, so you're right. So
is it that you have this combination of AK and A minus K, and somehow you're getting some non-Hermitian?
So what I'm basically saying is, if I just if I just say that X and P are the amplitudes for chain 1 and chain 2, right? So imagine I have two of these Hatano-Nelson chains. Right? One with the asymmetry going from right to left, one from left to right. If I just call X the average of A in chain 1, P the average of A in chain 2, I'd have the same equations. And all that means formally is that there's a unitary equivalence between this dynamical matrix and that effective non-Hermitian Hamiltonian for these two chains.
So you're like almost splitting, you're almost splitting a Hermitian Hamiltonian into two non-Hermitian Hamiltonians, something like that, is it?
Well, if you want, it's also just kind of saying, if I wanted to think about X's and P's as just particles, right, what does that mean, right? And it really means just having done this simple transformation of your dynamical matrix. But the idea is, in terms of the equations of motion, that looks exactly like what you get out of this. And the thing I didn't mention, but we've also done honest-to-goodness transport calculations where you inject light in the system, you see what comes out, you see this directionality. Okay, so this is even something that survives when you actually do couple your system to waveguides to put light in, take it out, it actually could be a kind of interesting, an interesting quantum amplifier even.
Okay, well, we've got a coffee break. So before that, let's thank the speakers for very nice talks.